Welcome to the third Microsoft Research India Vision Shindig. So what is Vision Shindig and why is it the third? So every 2 years, some of you may know that we have the Indian Conference on Vision Graphics and Image Processing that happens somewhere in India. Last week, it was in Chennai. And what we do is, as a part of that conference, there's been a long tradition of having about 4 or 5 internationally renowned researchers on vision graphics and image processing come and give plenary talks at the conference. And we have, since the lab started, which is 2005, so the first of these was in 2006, we have made it a habit to sort of piggyback on that conference and invite the distinguished visitors and some of our local friends and who are also equally distinguished, I should add, and other undistinguished people in the lab, and so forth, to get together, spend 2 days here, hang out. Mostly our goal is to have evening parties and booze and brains, but you have to sing for your supper kind of a thing. So all these people, in order to be entitled to good dinner and drinks and so on, they're required to give a talk. So we get them cheap, and we put them up in cheap hotels and take advantage of them while they are here. So that's it. And we have 6 talks. We try not to. What happened to the 6 talks? Chelappa is not. Yeah, there are 5 today. Oh, there are 5 today and then some number tomorrow. Okay, this lasts for 2 days. For some reason, I have the program only for today. It's online, right? Most of you know where to go find the program. I think it's research.microsoft.com/India and then search under events or something. Yeah, and the links from our web pages as well. Yeah, so the idea is the talks are 1 hour long, and then there is half an hour break between talks, and there is a lunch break. The purpose here is really not just to listen, but for all of us, low-life mortals, to have time to interact with these distinguished and extinguished famous people. And if you want pictures taken with these famous people, we can also facilitate that. Especially with Andrew. We have good cameras, so please let us know. And autographs and all that are allowed. So, without further ado, let me introduce Aaron Hertzmann. I introduced him 2 days ago at a conference, so I'll have to think of something cleverer to say, but it's really hard to do that. I was already very clever in that conference. But I think the most important thing to talk about Aaron is already in this title. It has rendering, photo, and science, art. So this is the 3 things Aaron represents. He's one of these people who have a unique combination of background in computer vision, computer graphics, and art. And he can tell you more about his art background. But I've known him for, say, 20 years or so, and right from the beginning, he's always blended smoothly his technical science interests with the art side, and can give talk to either audience as if he's the leading expert in that field. Okay, as if, but he might even be. At least in non-photorealistic rendering, I think he's the king. So, Aaron.
Great, thanks.
You have a mic.
Yeah, I have a mic. Yeah. So thanks a lot for coming. So in this talk, I want to do 2 things. One is I'm going to survey some of my past work in the area. I don't know how familiar people are with non-photorealistic rendering, so I'll give you a little bit of an idea of what that field is about. Yeah. Yeah, well, I can't do anything about that.
Maybe lower your mic.
Is there a volume?
Okay, while we are fixing the echo, let me say something that I forgot. Go ahead and fix the echo.
Test.
This thing was organized by our external research team, Vidya and Ashwani, and Manik, I don't know what role he played some kind of role, even though he's not part of the external research team. And so I want to thank them for their effort in organizing it and all that.
So there's 2 things I want to do. One is to survey some of the work that I've done in this area, and I'll tell you a little bit about my background. I hope you find it interesting. And the second, or sort of the latter third, it'll be a little more philosophical. I want to make an argument that this kind of research that we can do in computer science will reveal things about the way art works and will be fundamental to a new science of art. So that's more philosophical, and we can have a discussion about that later on. So how many people here have heard the term non-photorealistic rendering before seeing my talk title? Okay, and So about half. So there's definitely people who haven't seen it before, so that's great. I have something to do. So we normally think of computer graphics as mimicking the appearance of the real world, so making an image like the one on the left. You have some model of geometry and you want to make a picture of what it looks like if you had real lights and real textures and real scenes to put it in real movements. And for thousands of years, people have not always been focused on realism. There's another thing we can try to do, which is to try to make it look like a drawing or a painting or some kind of illustration that an artist might want to create. And there's a lot of reasons why we might prefer artistic rendering over a sort of steady, or like a grim determination to reality. Illustrators often prefer drawings over photographs because they can be used to convey what's important in a scene or to focus attention on important details. So like in automotive manuals and anatomic illustration books, you often see drawings in addition to or instead of photographs. For a lot of sketching and idea and concept design problems, you don't want to convey the illusion that you have the final answer. So like in architectural design, architects prefer not to have realistic renderings early on in the process. They want to convey, this is just an approximate idea, this is just a sketch, and if you give a client a rendering too early, then they will focus on real details that are not important to the conceptual design. In storytelling and in art, there's a lot you can convey through the visual style of a depiction that you can't quite do if you're stuck with reality. So you can convey, like on the left, there's a sense of lightness and sort of, a sense of whimsy about the scene that comes from the style of depiction. And on the right, you get a sense of the character in the scene, and that just comes from the way things are drawn. There's a lot of art and beauty that comes, again, just through the way things are illustrated. And the thing is that people have been thinking about non-photorealism for a long time, but it hasn't really kept up with realistic computer graphics. So in 27 years in computer graphics, we go from these ripples on a surface which were of a water, which were seen as like really revolutionary at the time, to like now basically if you have a movie studio with a big enough budget, you can pretty much do anything you want in terms of photorealism. So in terms of photorealistic graphics, if you have enough money, you can do anything. But for artistic rendering, there's still a lot we don't know. And to some extent, that reflects the fact that the physics of light is something we understand pretty well. And modeling it is just a matter of fast algorithms that model the simulation efficiently. But for art, what are the equations? What are the equations to describe a painting or a drawing? And that's a lot harder. So there's a couple of things that I view as sort of grand challenges in the area, that the problems that we as a field are trying to solve together. The first is, how do we automate something like a painting or a drawing? Like you give me a 3D model and I automatically produce a drawing of that model. And conversely, a sort of a complementary goal is to provide tools for artists. So if you're making a movie and you want it to look like a drawing or some kind of animated painting, you don't want it to be automatic. You want it to be something that artists or animators can work with and can control what the result is. But we still don't even know what the tools are to provide the best results. But if we can do that, every time people use new technology to create new tools for making art, we get new forms of art. And even now we see that the computer-generated animation is a form of art that didn't exist 20 years ago. And I think the same thing could be true for NPR, non-photorealistic rendering, in animation as well. Now, as I mentioned, I'm also interested in studying the science of art, and this is something I haven't done, but I hope to do. I hope we can do. And so this is not something that I think everyone shares, but I believe that this work is also about understanding how art works in an algorithmic way. And I'll say more about that later. And there's also, this is more of a technical issue for people in the field, but we as a field have a big problem in evaluation of these methods, and like, do we do user studies? How do we know if we can publish something which is good or not, or how do we convince people it's good? And that's a big issue that we have as a field. So I'm going to talk about two areas that I've worked on. One is painterly rendering and animation, And the second one is line drawing, and then I'll talk, like I said, about the sort of philosophical future directions. So a little bit about my background. When I was an undergrad in college, I double majored in computer science and art. The real reason I studied art was like, I was taking these painting classes, and there was this one distribution course in humanities that I had to take, and I hated it. But I found out if I switched, if I just took 12 art classes, I could get out of that one class I hated. So I was able to, so I did that. So what that means is that I spent a lot of time programming, and I spent a lot of time painting. Here are just a few more things I did. Nothing special, but just the kind of stuff that one does in college. These are from a program in Greece that I did. And then when I graduated, I had to figure out what I'm going to do after college. People said, "Oh, you're doing computer science and you're doing art, so you should be doing computer graphics." And I said, "No, those are totally separate things." And I was pretty sure I didn't want to try to be a real artist, because that's really hard. And I was really, having worked as a programmer for a long time, I decided I didn't want to be a programmer all my life, so I did go to graduate school in computer graphics. And I had to figure out what I wanted to do. And at first I was interested in computer vision. But then I attended this talk at SIGGRAPH 1997 by Pete Litwinowitz. And what he was describing, based on a classic paper by Paul Havery, was a method that was starting from a photograph and turning it into a painting. And he had a method that then was, the contribution of his work was to apply it to a video sequence to make an animation. And the way it works is it takes this image and puts down these little short hot dog shaped brush strokes all over the image. So each of these little strokes, the color of the stroke comes from the color of the image that underneath that stroke, and the orientation of the stroke comes from orientation in the image, the isophote directions, or take the image gradient, rotate it 90 degrees. And he was sitting up there and saying, "Well, I'm not an artist, and I don't really know how to do this, so I wanted to make this program which did this for me." And he said, he used words that say, when artists are placing brush strokes, that these are the rules that they use. And I was sitting in the audience thinking, that's not at all how artists work. And I went back home to my lab, or to my office, and started hacking and playing with that idea. And then I came up with this. So this was my first SIGGRAPH paper. And there's a few things which make it, building on his ideas, that are a little bit different. So what it does is it starts from that photograph, and it places these brush strokes. But rather than lots of little short dabs, it's placing long curved strokes that are roughly following isophotes in the image. That's the simplified version. And then, in addition to these long strokes, it is also doing it coarse defined. So when you paint or you sketch something, first you draw, so you get a rough idea of what you're doing, and then you fill in little details, and that's what this is doing. It starts with lots of really big strokes, and then adds little details to fill in to refine the edges. So you see big strokes in this kind of region, and little strokes where there are fine details. And you can change the styles a little bit. So anyway, so that was fun. Are there any, this is kind of a high level, but are there any questions? I guess it depends on what you mean. So if, now you could just read my paper and implement it, and you don't need a lot of domain knowledge for that. I think, if the question is how do you do research in the area, then I think you do need to have some idea, some mental model of what the painting style is that you want to implement. I don't know if that answers your question.
Yeah, this is sort of a Western style. There are obviously many, many different styles of painting. So that was more from that aspect. You want to research and create more of other forms of painting.
Yeah, there's so many aspects to painting. Like this is very surface oriented. There's nothing deep about it. And when you look at styles of painting that, like if you really want to model like the projection or the way things are laid out or the way composition is created, that's a much more interesting, deeper problem. And I think you need to have some understanding of composition to do that. It doesn't have to be technical, or somehow you have to be able to look at things and say, this is an explanation for what's going on there.
Do you have a page where you can just show the same photo with different styles?
On the web, well, let's see.
You're running it
I
real
can,
time, right?
yeah. It's on the web, and I mean there's some in the paper, but it's okay. I'll just move on. Okay, so that was. Let's see. So,
Sorry,
yeah.
I thought you were still searching. So I'm actually a newbie to all of this, and I don't really know much about it. Are there a set of rules for evaluating this that artists say, okay, so this is good and this is not good? So in the end, like when we'll end up with something, is there something quantitative that like the artist community or whatever in that area will say, yes, this is very good, and so you know you're making progress as you.
No, that's as I mentioned before, that's a big problem that the research field has, is we don't know how to evaluate this work. I can say a lot more about that, but the short answer is no, we don't know how to do it. And well, so in the early days, it's very easy to say, here's a new painting, and no one else can do anything like that, and any reviewer can look at it and say, wow, that's awesome, I've never seen anything like that before. But now, okay, here's my delta. This is a slightly different way of doing it, and now how do I convince a reviewer who may not have a very discriminating eye that this is better? And none of the obvious things. There's a bunch of obvious ways you could try to do that, and I don't think any of them really work.
But this is more complicated than that because now, as you mentioned, there's a human in the loop as well. You want to interact with the human being.
Yeah.
So,
and
another dimension.
yeah, so I think we're still, when it comes to interactive things, you can still show things that without this interactive system, you couldn't have done that before. I think in the end, in my opinion, the only way to evaluate that is to trust the judgment of the reviewers to say, this sounds like a good system and the results look really new, but it's a tricky area. Lots of people are asking for user studies at SIGGRAPH, and not just for this area, but for other areas. And people at SIGGRAPH don't understand user studies at all, so it's a big problem.
I think it's more generally, most famous artists died penniless, so the humanity doesn't have a good way to evaluate these things right away.
Yeah.
Takes time.
But they do after they die.
Yeah,
Yeah.
takes a while.
Yeah. I mean,
And maybe
So
in 100 years.
we should be killing off SIGGRAPH authors and then.
So one thing I would mention is that I think we went from having too much echo, maybe from the back, people can't hear your voice because. So now we all have to speak like Alyosha. What is advice?
yeah. And I'm feeling a little under the weather, so I'll try to have more energy. So I think we can talk about that more later. So I made an interactive version of it. Here there's a camera sitting below the canvas, and it just is capturing images continuously, and it just repaints the image where the video it's looking at has changed. So we showed at some art festivals, and so it's kind of an interactive version of the system. I was also commissioned to make, so there's a jazz musician in New York who was recording a video of his work, and he wanted to do something different with it, so we did this. So it's a mixture of JPEG artifacts, but you can see that it's, if you say, I wanted to make an animated painting from that style, it's actually really hard to do well. So how should the brush strokes move around when the video moves? That's actually a really challenging problem. So I don't think anyone could watch this style for very long, even though I think it's interesting. So then I started to think about, is there anything deeper going on in these painting styles? We're plopping down a bunch of brush strokes, and this very heuristic algorithm just iterates over the image and places strokes in certain ways. Is there any way we could express this as an optimization? And so what I started out with was thinking about as an energy function over a painting. A painting is a set of brush strokes with a linear combination of a set of terms. And there's just a few terms. One is just measuring the distance between the source image and the painting, weighted at edges. Something we want to panelize the number of strokes. In a way, we want a parsimonious code, or we want minimal number of strokes to represent the image, and we also want to cover all pixels. And so, given this image, the optimization algorithm, or the heuristic algorithm might produce this result, and the optimization would produce this. So this is much more parsimonious. and it follows the edges much more carefully. It took many, many hours to run on stock computers from 10 years ago. It's very inefficient, just a big hill climbing, propose a move, see if it improves things, and if so, keep it.
This looks much like a mean shift, but a mean shift segmental.
Yeah, it does. Except that there's strokes, but it has a lot of that, like the.
I'm saying instead of doing all that complicated stuff, you just applied a mean shift segment.
Yeah, well, but you want to end up with strokes in the end, not just. And in fact, some of the more recent NPR algorithms are based on like bilateral filter. You run a few bilateral filter steps, do a few other tweaks, and you get something that looks much easier than this. It doesn't have strokes, and you can't texture those strokes, but it works pretty well. So I think there's some common themes there. So one thing that we could do with this is to provide a little bit of artistic control by weighting different parts of the images in different ways. So in this, we might say, well, I have this scene, and I want to put more emphasis on the people, on their faces and their hands, and have less detail in the background. Or maybe I want to focus attention on the characters on the right, and have all of the detail over there. So this is just one sort of high-level way of providing control that you couldn't do with like a real pen and brush. So this raises the question of is there a real objective function that describes some style of art? And also, how do you animate these things? And these are really hard questions. I'll briefly show you some work that my current student is working on. This is an interactive tool. It starts with the video sequence and makes animations. And this is all using a tool which has lots of rotoscoping steps. So you trace out where people are in the video sequence, and you say, I want this style in this region, and it paints some strokes, and then you revise them. So there's rotoscoping just to figure out where the objects are. Then you run some automatic processing steps where you say, just run these styles over the image, and then you can refine the styles for individual parts of the image if you don't like it. Draw individual strokes or tell it to reduce. Like here, we're just adding specific strokes, I think. So this is keyframing new strokes. And we can get a whole range of different styles using this one tool, and you have some control over making the style animate in the way that you want. Unfortunately, I don't have this. So this is with a very different style with very large strokes. And there's just a few more examples. This is completely automatic. So I think with better tools and better interactive interfaces, we can get a lot more control, and we're making progress in that front.
So you use optical flow to answer your question about how to maintain the position of brush strokes.
Yeah. The strokes follow the optical flow. So here's the source, and the next one is completely automatic with no interaction, and the one after that is with some interaction. And it's kind of washed out on the screen, a little bit blue. I didn't find the right color profile, I guess. Okay. We're in time. Okay, so I think I'll skip this then.
You're going to skip that? That's what we all first heard about.
Okay. Well, it's just a few slides, so I'll briefly mention it. So here the goal is to learn things. So rather than use a lot of domain knowledge and try to build the best algorithm we can, we're just going to try to learn it from examples. So given an example of a photograph and a pastel drawing of the photograph, and a new photograph, we want to apply that same pastel style. And so here we start with so this is the full photograph, and then we were lucky to find an art instruction book which has this kind of drawing, and then we were able to produce this result. And this is the algorithm is very much like based on Alyosha's texture synthesis stuff, and he had roughly the same idea at the same time. And here's the result. And you can, I think it has a bit of the tension of it's both clearly a representation of that scene, but abstracted with the texture strokes, the texture of the pastel. And all it's doing is sort of copying different parts of this image in ways that reproduce this scene. Now, one thing is you can see that there's, it put these swan feathers in the sky, and that's, partly, it doesn't really know anything other than just match colors. And the nice thing is that with one algorithm, you can apply texture in lots of different styles. So this is a line drawing style applied to this butterfly, and then we get this result. The algorithm doesn't know anything about painting or drawing, and it's just copying texture. And that's all I have to say about that. So so those are a few examples of image processing to create painterly results. Now, the other thing, other main area I've worked in, big topic in the field is line drawing. And here now I'm switching gears in two ways. One is I'm now really focusing on line drawing and focusing on 3D models. And now we can actually, with 3D geometry, we can really think about how does the geometry and the nature of the scene determine where you draw strokes. And there was a lot more we can say about that. So, for example, the most basic thing that most people do is to draw the contours of the object. And these are a geometrically defined quantity. This is a set of points on the surface that the surface normal is perpendicular to the view vector. Or in other words, the tangent plane of the surface contains the camera. And so if you take this cow, and rotate it a little bit, and then render it, you get these contours. And so this is like the most basic version of a line drawing of a 3D model. And the interesting thing is that with this really simple formula, you actually get some explanatory power over line drawing. I mean, obviously we're not explaining everything in line drawing, we're not explaining much, but already here's a formula that does a little bit of line drawing. One thing we worked on here is in hatching. So we don't want to just have these outlines, we want to fill in the middle. And so we need to figure out two things to do hatching, two main things. One is we want to figure out the direction field of the hatches, and we want to figure out the tones, what the density of the hatches should be. And at this point, there had been a few previous things people have tried. One is to follow isoparametric curves on the surface, but these are really built into the way that the surface is designed, and they're not really generic for arbitrary 3D objects. And the other thing you could try, which is much more intrinsic to geometry, is to look at principal curvature directions, which if you're not familiar with differential geometry, it's essentially an intrinsic measure of the directions the surface is curving at each point. The problem with these is that they're not well defined everywhere. Like on a sphere, there are no principal curvature directions. And so to do this, we spent a lot of time looking at drawings. That's sort of the first thing you do, either as an artist or as a researcher working in this area, is you want to spend a lot of time looking at images. And so we observe a few common things among features of the images we look at. These strokes do sort of roughly follow curvature directions, like they're sort of circling around the sleeve or around his chest, but they don't really follow the fine details. So if they really follow the curvatures, there'd be a lot of squiggles in here, and they're much smoother than that. Here, the shape, the wrinkles are really conveyed much more with shading rather than curvature directions. So we started with these curvature directions, which are well defined in some places. So like on the arm, this direction field really circulates around the arm. But in other places, it's a big mess. And so we just run an optimization to keep the good ones and throw away the bad ones. And we get this, which is a lot more organized. And more technically, what we do is we look at points which are not umbilic points. So umbilic points, we throw away their curvature direction. The non-umbilic points, we keep the curvature directions. Those are points where the principal curvatures are not well defined. So like a plane or a spherical region are ones where the curvatures are the same in all directions. So if we start with just the raw principal curvatures computed by our numerical algorithm, we get the result on the left, and depending on the degree of smoothing, we can get the middle two results, the middle and the right.
So that's something, go back. See, the left one, right, has certain, that significantly changed in a number of places. It's not just smoothing up.
Yes.
How do you explain?
Well, so like in these regions, and there's a lot of singularities where we're just throwing those away because those are not meaningful. Those are just numerical artifacts essentially that are just accidents of the way that the mesh is represented, and we don't want to use those. And that's, so here, we're keeping these directions, and this stuff is just being completely tossed out. As for density, what we know with a lot of drawings we look at, there's a very simple rule that seems to be that it's just the simplest is just to base it on lighting. The darker parts of the surface will have darker hatching, and so we just threshold the shading of the surface into 3 levels, and we have cross hatching, single hatching, and no hatching for those 3 different regions. And there's more sophisticated things one can do, like varying the thickness of the strokes. So here's a typical result from the method. And so we get some of these effects of we have hatching around the boundaries, and we have the nice strokes curving around the wrist. Okay. We're now working on learning these methods from examples. So at this point, I think that this curvature-based direction field that I described is kind of like, it's been 10 years and there isn't really any replacement for it. And so we have now some work in progress where we have artists draw line drawings of 3D models. So like you start with this artist starts with this 3D model and they draw a hatching illustration of it. And we're using some methods from computer vision to learn these orientation fields and thicknesses and so on, and so that we can apply them to new meshes. So this is still a work in progress. But one thing we notice is that none of our models fit the stroke directions everywhere. In some places they're using curvatures, in some places they seem to be using isophotes and so on. The last technical thing I want to talk about, and I'm going to go into spend a little bit more time on this, is line thickness. And line thickness is something that's really important. It varies a lot, and it's really expressive. And it's something that most people don't pay a lot of attention to, at least in research. It's something there's a lot of expressivity in the variations in thickness. And it seems like a small thing, but I think it's pretty important. And in the research, the things people have used have been fairly simple. Like you just use constant thickness everywhere, or taper things according to depth, or just image space arc length of the geometry. And for me, the inspiration for I found this, I was looking on the web, on my friend's webpage, and this image seemed really inspirational to me. She was just playing with Poser, this program, for the very first time, so there's nothing special about the image. It's just some 3D meshes lit with rim lights, which are lights that are essentially off to the side of the image plane. And at least at first glance, some of these strokes, these rim lights, to me, they really look like strokes. So that's sort of the inspiration for trying to come up with a good model of line thickness. So the idea is as follows. We're going to start with a smooth shaded surface. And imagine if we were to threshold it. We just split it into dark and light regions. Now, it turns out that if we just draw curves along the middle of the dark and light regions, we get the contours and something called the suggestive contours. And just as an aside, the suggestive contour algorithm is, I think, one of the best papers in this area by Doug DiCarlo et al. And that's a really nice paper. And basically what it says is that, as I say, let me say this in a different way. Suppose you start with this image, and I tell you your job is to draw all of these regions with thin strokes. You can only trace strokes around the outside or on the interior, and you want to match these regions. And if you do that, you're going to get this image here. And this looks much more like a line drawing to me than the original silhouette rendering. And so our idea is just an extension of this in a way, that we're going to allow you to vary the thickness of the pen as you draw. So you're going to draw thicker strokes in parts of the image where this dark region is thicker. So technically, what that means is we have a contour, which is usually just the silhouette of the object. We can find the interior boundary of this thick region, which we call the isophote, and then we're going to draw strokes between those two curves that try to match the thickness of the region between them. And there's some analytic formulas for this for those who are interested. This is approximately inversely proportional to the curvature of the surface. the depth of the object, and the focal length. So what this means is that roughly objects which are thicker will have thicker strokes because they have lower curvature. Objects which are thinner have thinner strokes, and further away strokes will have thinner. Further away objects will have thinner strokes. No, it's including contours plus suggestive contours. They are, I mean, there's a couple of definitions. One way of saying it is that it's simply, I mean, one intuition is it's these strokes. So they're local minima of shading along perpendicular directions. Like the darkest parts of the surface, so the contours are all where n dot v is 0 for, assuming Lambertian rendering. And does that answer your question? Okay. Okay. So we can render these strokes in various styles. So here we're drawing lots of strokes with sort of variations proportional to this thickness. The brush style. And so we get these patterns of like more closer strokes are thicker than further strokes. Very thin parts have very thin strokes. So, to me, in a way, the interesting part about this is not just the algorithm, which I like, but how do we evaluate it? And this gets a little bit to Manik's question. As we were developing this method along the way, earlier versions of the system, we showed it to other computer scientists in our lab, and we were like, well, they seem okay, I guess. People couldn't really tell if they were good or not. And so we needed to find some ways of evaluating it or making an argument as to why this is a worthwhile approach. So the simplest thing you can do is try to reproduce existing artwork. So we hunt around for, we spent a lot of time looking at images. And one thing, we were able to find a few that we're able to reproduce. So this is from a graphic novel called Bone, and the student generated a 3D mesh. And when rendering the mesh with our method, we get this result. And we can then we can animate it, so we can see what that had. If we imagine that the artist had animated the character as a rigid object, this is how it might change. And we can also sort of plop it back into the original drawing. So it does a pretty good job of fitting this data. I mean, we don't know if the generalization is good or not. And we also found a technical illustration we were able to explain pretty well. So this is from a technical illustration that was made in the 50s. So this is a drawing. This is a line drawing that someone else made based on this. And then we built a 3D model and then generated a rendering of the 3D model. And it has a lot of the same variations. Here we put a light source off to the left so that we would get this same variation in thickness. But you see it has a lot of variations in common. But I would like to say that what we've done says something about lots of kinds of styles of art rather than just the ones we can fit well. And there's no way that we know how to simulate something like this. But we can say that there are some qualitative properties of this style of art that we do predict. And so essentially what we did is we said there's a bunch of things that our model predicts, and we're going to turn those into sort of qualitative predictions, and then we can find lots of examples that those predictions observe. Now, we are cherry-picking our data, so this is not a rigorous, there's no formality to our study, but I think this is an argument that is hopefully convincing, even though it's not quantitative in any way. So one thing, as I said, that in our formula predicts that objects which are further away will have thinner strokes. And this is something which one sees all the time, that this object is closer than that object, and so it has thicker strokes. And here, like this object, it's the same object as that one, but the strokes here are thicker. So one thing is that we don't know the geometry of these drawings. We don't know, or I think, yeah, here's another example. We don't actually know the 3D geometry of the world, so we can't say what the actual thickness was or the actual depth. But in some cases, we can say, well, this is the same object as that one, and it's further away, and it's thinner strokes, so that therefore it fits the model qualitatively.
So this may be a little bit back, one step back. But
Uh,
the examples you've shown are isolated objects, and this is not a very good example. This is a left. We also have line drawings where there are gaps,
Where they're overlap.
overlaps. Right?
Yeah.
So now if we take your algorithm of, let's say, immersion shading and these things, that might not quite work out, let's say, even if you had a 3D model. As that can work through that, and then there are usually issues when there are multiple objects.
Is there a particular effect that you're thinking of that occurs in overlap? Like haloing?
Some effect of interreflections between these objects, which will somehow get conveyed by the artist. And so for us to be able to reproduce that might take some time.
Yeah, I mean, there's all kinds of effects, like, how do you depict glossy surfaces and so on. And we're, this is, as with all science, we're trying to be reductionist and pick the most basic examples and try to find cases that we can analyze. There are lots of effects that are not being modeled. So with overlapping objects, one common effect is haloing. So like all of the strokes around the halo of this this foreground object are disappearing. Like these reeds don't extend into this object. So that's an example of overlapping that we're not modeling here. Something that might be fairly straightforward to add. Does that make sense? Yeah. Here what we can say is, well, this is roughly the same curvature and it's foreshortened, and so the strokes get thicker. So you see the whole goal here is a methodology that we're proposing, which is how do we take our mathematical model and turn it into predictions and then show where those predictions hold in real artworks. Now we also predict that thickness is inversely proportional to curvature, and actually it's a specific kind of curvature called radial curvature, which is in the essentially parallel to the viewer. Yeah.
So you've already checked it against real life drawings of real artists?
Well, I mean, that's what we're doing. And what does it mean to check it against these drawings? That's the question. So we can't measure the radial curvature of any of these objects, but we know that, for example, that the torso will have lower curvature than the legs, and which will have lower curvature than the arms and the fingers, and so the torso should have the thickest strokes.
I don't know much about this, but it could be that some artists do it this way and some don't.
Oh yeah. No, I mean, having spent a lot of time on this, we see every variation. Or not, I shouldn't say every variation. We see lots of variations. Some seem very sloppy. Some everything's the same thickness. Some it just seems random. But the claim is that these are simple predictions that occur over and over and over again. So this is not, again, it's not proof. It's an argument. So you see that we have big, thick strokes around the body, thinner strokes on the legs, thinner strokes on the horn, and so on. And like,
what about books which teach people how to illustrate? Do they have guidelines like this?
Some of these we've found, yeah. That's sort of like the first impulse of most people who work in this field is that, like, we'll just ask artists what they're doing, or we'll just read the books and we'll implement that. And it turns out that almost always, like, there's 80 pages on that are like, you just can't turn these things into algorithms. Yeah. And again, here again, yeah.
Can you just say, I want this thing about the curvature and stuff, is that a parameter in your model that you learned, or is that something that was intrinsically kind of part of the model?
So it's intrinsically part of the model. So there's a single...
So you already built that and then you're just figuring out the parameter.
So
couldn't you do model learning itself to see what kind of meta principles you're learning and then analyze the model?
Yeah. So the stuff I mentioned, which is in progress, we are actually learning thickness from hand-drawn illustrations. But here, but when we do that, we don't get any principles out of it. We don't really get any principles. So in the other method we're using, I can't remember now if it's Lasso, L1, or AdaBoost. But so we get a whole bunch of features, and it selects these features and not those features. But that doesn't tell us any principles as to here we're looking for like a core theory that explains some phenomena rather than an algorithm.
Decision tree, that might be more
Yeah, but when you fit these sparse methods, including decision trees, you get, it says if this thing is greater than that, then you do this, and you can't interpret it in a simple way. Yeah.
So there's this British children's author, Quentin Blake, right?
Mm-hmm.
You're probably familiar with him, and he wrote a book that teaches people how to draw in his style,
Mm-hmm.
and he starts with very simple objects, from non-rigid, rigid objects, then dogs and cats and stuff like that. Do you think you could ever teach like a system like that, sort of in drawing complexity, how you can basically map objects into a certain style?
I think it's really hard because when you artists draw, like in those instruction books, they're using so much knowledge that you have about how things should look and what the types of objects are. Just a simple, okay, let's take this for example. If you had a 3D model that was exactly like that, then it's trivial. But if you say, let's take a real tree, and then you're supposed to figure out that it should look like that, that's a really hard mapping to learn. Skip this. Oh, actually, so here this is the forearms. The wrists are typically thinner than these bulges. They have the wrists have higher curvature, thinner strokes. Yeah.
So you have an assumption before, arms are, legs are larger and arms are heavy.
Okay.
But when they are using these graphic novels, they try to do something like comic characters won't be having something which is generic. So how are you relying on that feature?
They have something which is what? Generic?
So like this character, say, there is a character. So the legs are really very thin here, but the arms are.
Well, yeah, exactly. So the arms. Oh, yeah. So here, but it's clear that these arms are much thicker. So this is not a typical anthropometry. Most people will not have gigantic arms.
Yeah, but so how do you come to that prediction or like assumption that you make say that large torso are?
Yeah. So what the model predicts is that thickness is proportional to curvature. So in most cases the arms are thinner than the legs, and when that's true, the arms will have thinner strokes. Here, that's not the case. So the model is still here, where we have big fat arms and thin legs. The model would still say that these are thick strokes. The arms should be thicker. And one thing the model predicts is that above your cheekbone you have like the radial curvature, like things are very foreshortened, so you should have thinner strokes. So this is a rendering, and actually we see this all the time, that right above the cheekbone the strokes get thinner. There's more technical things. There's a bunch of other things which probably not that interesting. Strokes are limited in how thick they can be. Lighting affects things, so when light source is off to the left, you can see there's a shadow here, we get thicker strokes. So here the light source is probably above and to the left, and so we have thicker strokes in the bottom and the right. This is a drawing, obviously. The strokes in the interior should be thinner than the ones in the exterior. And that's quite common. So even with these, which have a very sort of mechanical style, so here there's very little variation in thickness, but the exterior silhouette strokes are thicker than the interior strokes. So again, this is an attempt. So there's two parts to this work. One is just to come up with a model, but then to figure out how to make an argument, to try to convince people that there's something going on here. And so that brings me to the final part of the talk. So those are all the technical things I wanted to show. And now I wanted to discuss how I think these technical tools can be used to develop a science of art. And so right now, as I mentioned, most people, I think almost everyone working in this area, we view ourselves as addressing one of two problems. We want to make tools which are automatic, that make it easier for novice users to make nice images. And we want to make tools for artists that will create new art forms and allow them to express some new thing that they want to express. In the science of art, I think we can think of there as being two fundamental questions. One is the generative model. How do artists create imagery? And the second is, or we might think of a functional mapping, which so it goes from a photograph or a scene or something that you look at and produces an image. And second, how do we respond to imagery? So given an image, is there some function that tells us how good is it? How much does it express this emotion or that emotion? So in other words, we imagine there being some function in the brain that takes an image and converts it into a response. So, and my hypothesis is that these computer tools and non-photorealistic rendering will play a central role in the scientific understanding of art and illustration, specifically visual art. I think that if we do this, we could, in computer science, or in computer graphics in general, we're always, wringing our hands about what are we doing which is scientific. And I think this is a way in which computer graphics can directly further human knowledge about fundamental aspects of humanity. If we understand art better, we can build better tools and potentially broaden the scope of art and illustration. So right now, people have studied art for thousands of years. And there's sort of two principal ways that people understand art. One is through art history and through criticism. And I guess whenever I try to read these things and try to turn these into an understanding of the visual process, the explanations are extremely vague, and they kind of make sense, but they're not. I don't think that art historians have a language which is technical or very specific that allows you to say really specific things about what goes on visually. Well, it's a good thing there's no art historians in the room because I need to find a more diplomatic way of saying that. But there's certainly a need for a more technical language. The other is art instruction. And when you read art books or take art classes, you're given a lot of information. But one of the jobs of an art student, one of the things that is hard about it is to turn what you're told into practice. And just interpreting art instruction, what they tell you, that's not easy. It's definitely not something you can turn into algorithms. The art student does a lot of work to interpret ideas and turn it into their own procedure. Now, people in the more mainstream sciences are starting to look at art a little bit. So the people who, like Ramachandran and Hertzmann, have some sort of neuroscience theories of effects like peak shift that we respond to comparisons, which they use to explain caricature. But they're very descriptive principles. They don't really tell us how to make anything. And there's now fMRI is like the popular thing to do. So now you stick people in scanners and measure which aspects of the brain respond to beautiful versus ugly. But again, this isn't really a very descriptive model, but it's certainly interesting. Now, there's also...
You also just learn from watching people draw. So I guess if you're at Adobe, you know exactly how people go and what brushstrokes they use, all that data must be stored somewhere.
Yeah, all that data is available, but what's the model that you fit to that data?
No, can't you try and learn something from that itself?
That's like asking you watch someone write a novel on their word processor, and you have the whole history of all the edits and changes they made to the novel, and can you learn storytelling?
Principles on that, right?
In fact, maybe by watching all the strokes that people use when they use Photoshop, can we actually learn to create new art using Photoshop?
So I think it's really informative. I think it's difficult to turn those measurements into models. But yeah, I would certainly.
Saying that Nuria already did that.
No, but she did this work on learning painting styles. You could have a fun block painting.
So that's the image analysis. Nuria actually worked with. It's what she worked with them. That's just copy paste.
Yeah, that's just texture. There's people who are using natural image statistics to do forgery detection. So you run your image through some Gabor basis functions and estimate some sufficient statistics, and then build classifiers that tell whether this is a Van Eyck or not. But those are obviously not generative. So we can think of there being descriptive models, like, so in art history and criticism, it's both qualitative and descriptive. They say, when the surface curves in this, or when you're drawing an outdoor scene, then you might want to kind of do this sort of thing. Art instructive and generative, it tells you how to make things, but it's qualitative. It doesn't tell you how to build algorithms. The image statistics and forgery detection stuff is quantitative, but it's descriptive. It doesn't generate anything. In NPR, the kind of stuff I've showed you about is both quantitative, like it predicts specific numerical quantities, and it's generative. It tells you how to make things. So what does it mean to explain, what is a model of art? So I mentioned before these simple painterly rendering algorithms. So the most classic one is a paper by Haberle, where it is an earlier version of my stuff, or my stuff builds on this, where you start with a photograph, and you plop down a bunch of strokes in some random set of parts of the image. And now, in a way, I would say this is a simple model of painting. Now you say, well, this is terrible. This doesn't look anything like a Monet or a Renoir or whatever. But on the other hand, with this incredibly simple algorithm, virtually everyone recognizes this as an impressionist painting. It's clear, it looks like a painting. It doesn't look like a great painting or any specific painting, but with a five lines of pseudocode, you have something where everyone recognizes this as a painting, and that I think is extremely promising. It really suggests that there is a model here. And likewise, this is using contours and Doug DeCarlo's suggestive contours. A very simple, you can describe the algorithm in a one-line definition of these curves, and you get things which look a lot like strokes. It's not a model of everything, but it's a really nice model. With all, in all science, you have to start with simple models of the world. And one way of thinking about these things is that traditionally science is viewed as having two pillars. There's theory and experiment. You come up with theories, and you do experiments to test them. And nowadays, both of these things involve computation fundamentally. Some people think that computation is a third pillar of science, some don't. But regardless, everything people do from protein folding and bioinformatics and weather prediction and quantum mechanics, computation is fundamental to developing theories and testing them. And the same, I think, could be true in art as well. So we can come up with theories, either art historical theories or mathematical theories, and we can test them through computation. We can implement things and run them and see what they do and see if they match results. One other side of this, there's some really nice work by Forrester Cole, who's now at MIT, where they have they take 3D models and they print them out, and they have artists draw line drawings, and they see if the line drawings that people make match the algorithm developed by the different methods. And decision trees is one of the methods they use to model this data. And they're able to, with simple models, to say these kinds of curves match what people do and these ones don't. And they found that the curves that we have, like the suggestive contours, they match about 80% of the lines that artists draw. And there's very specific places they can identify that are not modeled by the current methods. So I guess we already talked about this. There's this issue of how we do experiments. And as I said before, I don't think we as a community really understand how to do this. And this is, again, we talked about this already, so I won't say any more about that. The one point is that we're not trying to model everything. We're not, if we have an album, we don't expect it to replace a famous artist. We expect it to model some aspect, and as we go along, we add bricks to our cathedral. We model more and more things, and the more we learn, the better. In biology, there's a notion that people can be modeled as optimal, and animals. There's all kinds of different aspects in which foraging behaviors and movement, bone densities, all of these things are viewed as optimization processes. Now, optimization, evolution is not truly an optimization process. It's a controversial notion in biology. Some biologists think that everything is, random. But I believe that optimization provides a model, a valuable model. It doesn't explain everything, but it explains a lot. And we can use the same ideas in NPR as well. Now, what the evolutionary role of art is not so clear. I think more in terms of people learning. Learning is more of an optimization process rather than evolution. with respect to art. So one value of optimization is we can get to higher level principles. So most of the work in this area is very algorithmic. Like even some of the stuff I showed it's basically you do this, and you do this, and you do this, and you do this. It's not a principle behind it. So we might say, instead we might say, maybe there's a response function. There's some, the viewer viewing an image generates some response in the brain, and the goal of the artist is to produce an image that yields some desired response, conveys a particular scene, produces a sense of emotion or a certain set of responses to an image. And as I mentioned before, the most basic thing that people have done is not quite that, but a simpler thing, which is to say, I want to produce a result which is close to a target image while still somehow minimizing the number of strokes, and in so doing looking like a painting or a drawing. This can be viewed as kind of a proxy to the notion of the response that you get. So this is sort of saying I want the viewer to view it as a particular scene, and this one says I want it also to look like a painting or a drawing. But it's obviously a limited approximation. The nice thing about optimality is it allows us to reason about what the goals are without thinking of the optimization process, the mechanisms. But on the other hand, it's really slow. It looks like I'm running out of time, so I should move ahead. So one other thing I want to mention is that we can view we're Bayesian. We can view the brain as having a set of hidden variables with respect to the scene being measured both in terms of low-level shape features and high-level recognition. And there's uncertainty over these variables, and so this uncertainty itself can be interesting for art. So this object is very clear what object it is. This object is probably a bad image because it's very vague. There's many things it could be, and you can't tell just from the drawing. The Necker cube is interesting because it's ambiguous. There's two interpretations that are bistable. You can go back and forth between them. They're both very strong interpretations, but it's ambiguous which one is right. It's not beautiful, but it's interesting. It's something that it keeps your attention because it's interesting. And so some images like this, so this is an Arcimboldo painting, Arcimboldo from like the 17th century. It's much more interesting because the two interpretations are really strong. It really looks like a person, and it really looks like a bunch of fruit because shading and shape and texture and all these things are sort of marshaled towards creating these two different interpretations. And here there's sort of a sense of unease that comes from uncertainty. One interesting observation is that the primitives that people use in art and NPR sort of seem to match the ones which are sort of foundational in vision. So edges and segments are things that are sort of fundamental to lots of drawing. And there's maybe an interesting correspondence between the primitives that people use in art, in a lot of kinds of art, with the primitives people study in vision. One thing we don't do now is anything high level, thinking about what the goals of the work are, and as you vary your goals and say focus attention here versus here, you get different results. One thing is, so when I was taking this painting class in Greece, this is what I did in the first day, and the art teacher the professor came back and said, "This is horrible. Why did you draw this street sign here? It doesn't add anything to the image." Or you don't have, just because it's there doesn't mean you have to draw it. And I was thinking, well, I want to convey the scene as I saw it, and I didn't understand. It didn't make any sense to me why I didn't draw this. After spending a lot of time in this program, at the end, I was making more abstract paintings, and I don't know why. Like, I don't understand. I'm still, after 15 years, I'm still trying to figure out why is it that you don't want to draw that street sign, but you do want to draw like this grill pattern. Like, what determines what things you keep in and what you leave out? What's important? And so these high-level decisions, I think, this visual processing is a part of this. These are all really interesting questions, I think. So, all right. So, sorry for going really way over time. I think that, well, in short, there's a fun area. There's really open, interesting, challenging problems here. We have an opportunity to really further human knowledge and understanding what makes art in a way that no one's ever been able to do before. So, thank you for your attention.
I have one question to ask, and this is going to completely challenge everything that he has said. Now, in the spirit of good scientific debate, I'm not going to ask the question. I'm going to illustrate it with an example. Right? And the point is to find out how most of what Aaron has talked about today is not founded on any basis.
Sorry, what's the point of that?
Did you know this?
Yeah.
So apparently this was decided yesterday. I want to correct you.
Oh, thanks.
So, this is all that we just found out yesterday Aaron was selected for this award. So we're privileged to have him as one of our guests. It's kind of a nice place. Sorry, it has nothing to do with
Okay,
it.
thanks.
So, Aaron, what you're talking about is basically, on some level, it is going around the actual pixels and going directly into what the brain perceives. So it's very, very much perceptual, right? So, for example, one example is this line drawings, right? Line drawings don't occur in nature; they don't exist, and yet we are perfectly good at understanding them. Or the two-tonal images that I guess Toulouse-Lautrec came up with, right? They are completely surreal, unreal, right? And yet we see them. So, do you think that this is really MPR is basically a vision complete problem, that you really have to go all the way to understanding, to have a model of the scene, to have a model of objects, and only then can you actually kind of really produce scenes that people react to in a similar way.
I think that doing everything is vision complete. So if you wanted to completely reproduce everything, then you need to have a model of the relevant parts of visual processing. But you can abstract out parts and say, okay, I'm just going to assume that lines are the right primitive, and then do everything based on that. So there's certain things you can do along the way without knowing all of vision. There are some things that you would need to know something about vision to solve.
But I can actually argue, Alyosha, that in some sense it's beyond vision. I mean, that picture he showed gives you a sense of unease.
Right.
I can't imagine a vision program.
Oh no, that one actually is very easy because it's a multi-perspective panorama.
But multi-perspective doesn't create unease. Multi-perspective doesn't.
Because you have two horizons instead of one. That's just wrong.
I think of it. I was thinking more like the shadow.
No.
Yeah.
I'll explain to you. Mona Lisa has the same issue, right? You have on the left side of the Mona Lisa and on the right, the horizons are at different levels, which basically means that you don't have a good estimate of the height of the viewer.
No. So in other words, where I was going with it is that some emotional reactions that these paintings invoke may not be captured by vision algorithms. But what you're saying is they just reduce to a bunch of features in the rendering.
So does Mona Lisa give you the same sense of unease and complete same emotional response as the one that I showed?
Well, okay, I'm not.
So to me, it's a little bit like if I listen to a story, right? Like when they tell you scary stories, dark evening, etc. It gives you a sense of unease. You look at the picture, it does. So they're connected at that level. I'm not sure it's the features of the painting that capture the unease, but rather the setting of the scene. So it's more than vision complete.
But you're making
AI.
Well, yeah, okay, it's AI complete. Sure.
Yeah. Or maybe vision should just grab more territory and say understanding the aesthetic and emotional response is an important part of vision.
Sure.
Oh, yeah. This makes this artificial distinction. You're kind of making an artificial distinction that vision somehow is disconnected from the reasoning of what you see, or that can even be accomplished without that kind of reasoning.
Yeah, but I don't see any ICCV effects talking about unease and so on.
Well, people do talk about predictions and threats, and some of it is not obvious in the.
Sorry, perceptions and threats?
Predictions is part of the vision.
No, I didn't hear what you said.
So I'm saying that the reasoning and the perception of just the physical entities there, to define vision to be some sharp boundary, not right to start with.
Yeah. And there's a bit of work that is now looking at aesthetics. I wouldn't say it's going very far as ICIP or ICPR type papers, but more of that's going to happen.
So how strongly can you model art? Like, is art not too subjective for fitting a model to, however good you do a job, figuring out why things look the way they look? But
there is some subjectivity still.
Yeah, well, there's a lot of subjectivity, and part of the challenge is to either reason across it, find things that are common to a lot of, lots of people like certain kinds of things, and so what can we say is common to that? Or can we describe the space of preferences and styles?
I'm going to actually cut off the discussion only because we have to have some break so people have a chance to come and informally talk to you all.